So, so let's just jump in. We'll try to keep this within an hour. I think that'll actually be pretty easy to do. If there's, but it depends on how many questions there are. So, two things we're going to cover. I always you see technologies, or we all see technologies go through the hype cycle. I think probably the last big hype cycle was big data and all the stuff around that. Some of it accurate, some of it not so accurate. I think machine learning is probably, and data science in general, probably one of the. I don't know if we're at the top of the hype cycle yet, but I enjoy taking these technologies and taking some of the hype and mystery out of it and just looking at, okay, what's actually really involved in this? Is this an old idea? Is this actually something new? Or is this an old idea that someone has just attached a new name to? In some cases, like I always think of big data, that's something old that someone's just attached a new name to, right? But some things you actually find are somewhat new or have some new developments that bring a new usefulness, enable you to do some things that you maybe couldn't do before for usually technology reasons. So let's jump right into it. Let's demystify some of this. Here's the breakdown. You've got the field of data science, which includes probability, statistics, includes a lot of things. So kind of the basis for it is probability and statistics. Within one leg of data science is focused on predictive analytics. You want to be able to do analysis that enables you to predict certain things. And within that, one of the tools that you use for you can use for predictive analytics, and the one that's surrounded by lots of hype cycle right now, is machine learning. So, what exactly is machine learning? What's a layman definition? It's creating a predictive model by showing it, and this is one definition, by showing it data with known answers. There are some exceptions to that, and we'll talk briefly about that, so that you can then use it to make predictions about data you give it where you don't know the answer. So you train it with data that has an answer, and you validate it with data that has an answer to see how accurate it is, and then you use it on data where you don't know the answer. So that's a pretty succinct definition. So there's not really any science fiction around this. If you want some rocket science, you can find that here. This is the study of probability and statistics, and you have a variety of different probability distributions, some discrete, some continuous, some, you could spend years studying this and probably still not know everything there is to know, but you can kind of, at a high level, it's good to understand the basics. Most things in our real world tend to fall into something like a normal distribution is one of them. Hair color, body weight, height, those sort of things. Illness, severity. A lot of those things tend to fall in a normal distribution. Some things, cues, things that involve cues, traffic, computer, memory cues in a computer program, line at the grocery store, anything that involves cues, those tend to fall into an exponential distribution. That's normally how things arrive at a cue. There are things that might be mostly normal but kind of shifted, like a log normal or a Weeble. There's a whole field in fitting this. Now, back when I was studying this for an engineering degree, we didn't have a lot of software to do these calculations for us. So, a lot of times you had to do a lot of it by hand, which is both good and bad. The reality is that computer programs are a heck of a lot better at, doing software, doing math than I am. They don't get distracted as easily as I do. So one of those languages that allows you to, that's purpose-built for statistics, probability, and, numerical analysis, that sort of thing, is R. It's free, open source, it runs on just about any platform. It's been around for about 27 years. It was developed by statisticians for statisticians, that sort of thing, very purpose-built. Strong community. It's got packages for everything you imaginable. Just about anything you can imagine, there's a package for it. It might be great, it might not be okay, it might not be so good, but there's probably a package for it. Along with Python, R is probably, I would say it's second by only an area margin. It is one of the most frequently used languages in data science. So, and some people naturally gravitate toward Python, some people naturally gravitate toward R. You tend to see the data scientists gravitate toward R. You tend to see software engineers, developers gravitate toward Python. I'm not sure there's lots of debate about which is better. I don't know. They're both good. If it gets you where you need to go, use what you need to do that. So, what do you need for machine learning with R? Well, you need R. You need a package called Carrot. That's a good way to get started. It's got numerous machine learning algorithms built into it, and it covers both continuous and discrete types of probability distributions. For this example, we're going to use the IRIS data set, and Brent, you've probably seen this before. Jacob, I'll bet you've seen this with Python. This data set, and we'll actually dig into this just a little bit. It's 150 rows of sepal lengths and widths, petal lengths and widths, and the species of iris that those four measurements map to. So let's jump right into that. If one of the things you have to do in data science is understand the data that you're working with reasonably well. So let's dig into what exactly this iris data set is. Iris is actually a flower, and the measurements that are in this data set are of the sepal, which is it's the structure of the flower that has the reproductive organs. So the sepal, the length measured, and the width measurement. And then a petal, which is the part of the flower that does not have the reproductive organs, does not produce pollen, that length and width of those. So that's the type of data that we're working with. Now, you've got those four measurements, and you've got the species that they map to. It's one of three: Setosa, versicolor, or virginica. We've got the measurement, those four measurements, and the species all as a row. That's what the data set looks like. Let's take a look at it. Here you see it. This is like the first 15 rows. Sepal length, sepal width, petal length, petal width, and then the species that was measured on. So these are actual measurements. These are observations made in the field, and the species is the known answer in this case. So in probability and statistics, you would call these four measurements are the independent variables, and the species is the dependent variable. Or you would call these four measurements are the features, and the species is the label. Those are the terms that you'll typically hear around this kind of stuff. So, the questions, so a little pause, why don't we just, you hear all kinds of answers from various people, around how you would actually use this. If you go back and look at this, in theory, conceptually, it's not that difficult to understand that, hey, okay, I could use this piece of knowledge to take four measurements I've given and predict what the species is, right? That's the whole purpose of what we're going to do today in this hour. Now, you always have those questions of, okay, are there other ways we could do this? Can you do this with a formula in a spreadsheet, or can't you just write some code with some if statements and, or I needed an equation, to handle this sort of thing. Those logical constructs, formulas, stuff like that, it's deterministic. If you give it the same inputs, you're always going to get the same answer out of it. When you have to consider uncertainty, you have to bring in probability and statistics, and those are stochastic models that consider probability and statistics. So predictions are normally, about anything in our real world, those predictions are normally going to be stochastic models. So this is why, or this is one of the reasons, you would use something that relies on probability and statistics to make predictions. And in the pragmatic sense, would you really want to write a spreadsheet formula or a code with a bunch of if statements? You have to rewrite it when the data or the distribution of the data, as that changes. So it's much easier to just retrain a model. That's the pragmatic reality of it. So in the end, so the answer to this is really, you can think of a predictive model. You could think of that as almost like an equation that considers probability. That's the way I choose to think of it. I think that's a kind of a good analogy. So let's take a look at some summary statistics of the IRIS data set. So you've got those 4 independent variables across the top: sepal length, width, petal length, width. You've got some basic statistics about them: mean and median, first quantile, third quantile, mins, max. You've got the 3 labels, or 3 dependent variables. There's 40 samples of setosa, first color, virginica. So that's pretty clear. Numbers are sometimes hard to look at it, so let's look at it graphically. We did a feature plot for the independent variables. So you've got 4 input variables, 4 independent variables, so you've got 4 graphs. Each color is a species. So if you look close, so look at the blue. Look at the blue line here, the blue graph. Now this is petal length, petal width. Looking at the blue, this one doesn't overlap. This one doesn't overlap. If you look at the other 2 species, the purple and the green, those overlap in terms of petal width. But you can actually look at this graph and see how you could go about making a prediction. If you're handed 4 numbers and the petal length is less than 2 and the petal width is less than 0.5, and the sepal width is somewhere between maybe 2.5 and 5, and the sepal length is somewhere between 4 and 6, you could probably make a pretty accurate prediction off the top of your head that this is a setosa. The species is setosa. Now, what we can't do as humans, without crunching a bunch of numbers, is handle these where there are overlaps. You can see where the purple and green here overlap and the blue overlaps, and purple and green. This is the kind of thing that a prediction model based on probability and statistics is good at. So even though there's a lot of hype cycle around machine learning, it actually is something useful. So any questions? Any questions yet? Is this all kind of making sense?
Yeah, it looks good. And it is the same data set I've used in other R training classes.
IRIS, yeah, it's pretty common. I figured it was a good one to do an example with, because it's easy data to understand. So, the point you should get from all that is the other thing we should look at here is what probability distribution do these fit, right? I don't know. It looks maybe normal is probably a good approximation. Maybe Weibull or log normal might be decent approximations. It's somewhere. It's something that we can work with in R and have some confidence that we're probably on the right track. So something important to note: the better you understand the data, the better the prediction model is going to be, and the better the predictions that come out of it are ultimately going to be. And as an example, I think I've already said this, but I'll say it again. What we're going to do is take four input variables, 4 measurements, features, independent variables, whatever you want to call them, and we're going to use that to predict the species of IRIS, which is a classification. It's the dependent variable. That's the species is the dependent variable. So which category of machine learning are we looking at? So this table gives you a few different, quite a few different terminologies here. So what do we mean by discrete or continuous? Continuous, you want the output to be essentially a numerical value, like a probability, an interest rate, height prediction, something like that. It's a numerical value. Discrete, the output of that is going to be generally a classification. It's going to be A, B, or C. That's what makes it discrete. Now on the top we got supervised learning and unsupervised learning. What does that mean? So in this example, we're going to do classification categorization, right? That's supervised learning because we know what to expect, what kind of outputs to expect. We know that we're going to train it with 4 pieces of input data, independent variables, 4 features, and we already know what the labels are. It's A, B, or C. It's Setosa, whatever they were, Setosa, Virginica, or Versicolor. We know what the labels are. We know what the dependent variables values for those are. If you don't know what you're looking for, then that is unsupervised learning. So in our case, if we had this set of data and we did not have the species classifications, but we were looking for some way to get some sort of clustering out of this, that would be discrete unsupervised learning. We could hand it that data set and go, okay, so classify this into A, B, and C, right? In unsupervised learning, you don't know anything about the output and you're trying to discover some sort of output. Supervised learning, you already know what the form of the output is going to be. You want to be able to predict the individual values. So we're going to focus on that classification categorization. Now, you have to know that because you have to pick the right algorithm and use it in the right way to do this. So species prediction, this is a classification model. So we're going to get 4 measurements as the input, and the output is 1 species prediction, essentially. So since it's a classification model, we have to use algorithms that support discrete supervised learning. So there's 5. There's 5 we're gonna try. Linear discriminant analysis, which is very similar to linear regression, except it's used for categorization instead of predicting a continuous numeric value. Classification regression trees, k-nearest neighbors, support vector machines, random forest. All these have their similarities and they have some differences in how they go about it. These are the 5 algorithms that we're going to try training. Now, how do we get started? So if you're doing this yourself, which you've got the code in this presentation that you could, you got to install R if you don't already have it. It's pretty simple and painless. RStudio is pretty nice, gives you a GUI, a pretty good GUI user interface around R. Inside of R, there's 2 packages you need. One is Caret. We'll use that for the machine learning exercise. And then we're going to look at what you do with this predictive model once you actually have it and you're happy with it. So go ahead and install this REST R server. We're going to use that to serve it as a REST API. So let's set up the parameters. So we've already examined the data. We did some sampling. We looked at it, at some subset of it. We looked at some summary statistics and graphs. We think we understand it. This is pretty simple domain material. It's flowers, and we're going to predict which species based on 4 measurements. Now, something you normally do is split the data set into chunks. So we're going to start out by splitting the data set into 80% and 20%. And we're going to take that 80% and use that along with cross-validation to train those algorithms, those 5 algorithms. And the cross-validation will give us a read on the accuracy of those. We'll look at that in a minute. We're going to hold on to that 20%, and we're going to use it to explicitly validate one of the best trained model to see. We're going to give it data that it hasn't seen before and let it do predictions, and then we're going to compare its prediction to the known, the actual known value. So we're going to use tenfold cross-validation, and what that means, you can think of that as splitting that data into segments, and you're going to take one of those segments and actually use it for a validation, what I just described, feeding it the data, seeing what the prediction is, and then comparing that to what the known value is, and then use the rest of it to train the model. And by tenfold cross-validation, what it does is it'll take that slice it's using for validation, and it'll move it. It'll pick a different slice each time, and it'll do it 10 times. So that's kind of what that means. The metric, this is a classification problem, so the metric we are interested in is accuracy. So let's move forward. We're going to train the algorithms. Now, we'll actually go to R and step through this. So, and that's probably a good time to ask questions if you have them. So, you want to see the algorithms the same. That way you get results that are in the same scale. And you also make this, this training exercise, training the algorithms, you make it a repeatable process. So here's what the R code looks like essentially to train, these different models. This is what we'll run. It looks pretty much the same. We're sticking the model into a variable, and we're passing it the data set that we're using, the one that we trimmed down to 80%. Here's our training control and the metric we're interested in, and this is the class that we're interested in, the label that we're interested in. So we're going to make these calls with all 5 of these algorithms. Oh, by the way, so I noted that R is a mostly functional kind of programming language. Here's one of those areas where you see this. So if you look, if it were a what is the word? Not functional programming language. Someone help me out if you know the word. You would call this function, this train function, once with each row, right? But you don't do that. Here's where it takes a functional kind of perspective. You're calling this function, you're handing it the whole data set. And you could do that 5 times. Or you don't want to do loops in, except for real simple stuff. Like we could have looped these 5 training functions and call them with a different method. That's an okay kind of loop to do in R. You wouldn't want to try to do something like handing it 1 row at a time, though. If you're handing it a data set, you want to hand it as a chunk. So you call a function, you hand it the data set, and you get an answer back. So that's that's a functional approach. One of the main concepts is it avoids loops. So we trained them. We're going to look at the resamples, which is part of the validation process. Stick that into a variable called results, and get summary statistics of those, right? Here's what the accuracy, so for categorization, you're going to get 2 numbers, accuracy and kappa, which is a reliability coefficient for the categorization. Look at the means column here. Looks like LDA had a 97.5% accuracy. Random forest was next up, 95% accuracy. Look at the kappas. Look at the means. That's probably the most telling number. LDA looks like it had the highest mean. Random forest and KNN were about the same. They were the next up. So, we probably wouldn't want to use CART. That looks like it's the lowest accurate, lowest kappa, and probably looks like it's the lowest accuracy. LDA appears to be the winner for both accuracy and kappa. It's hard to look at numbers. Let's look at a graph of that. We've graphed accuracy and kappa, the reliability coefficient. For LDA, you've got the different models down the side. LDA, here's the one that visually confirms that this is the best model, right? You can see The mean here is the one. It's the one whose mean is closest to 100% to the 1 mark. You can also see its range from high to low is the smallest. So it's the most left and shortest graph, dot plot. The kappa has the same thing. Out of all these, its middle dot is the farthest to the right, and you know, its range from end to end is the smallest. So we've kind of visually confirmed LDA, linear discriminant analysis, certainly appears to be the best model with the data. You know, it's the algorithm trained with the data equals a model. So it is the best model in this case. So let's take a closer look at LDA. Let's take that 20% of data that we held back for validation. Let's take that. Let's run it through the predict model, or let's run it through, give it to the predict function, hand the predict function that model that is the best one, the LDA, and give it the validation data set. And we're going to store that in predictions. All right. Now, we're going to wrap a confusion matrix around predictions, which is that's the species, the list of species that the model predicted, and validation dollar species, which is the list of known species. And the confusion matrix for a categorization, confusion matrix is going to tell us how these matched up. So Setosa, you see all these, well, actually for each class, for each species, Setosa, Versicolor, and Virginica, you see all these ones in sensitivity, specificity, positive predictive values, negative predictive values. You see all the ones. That's really good. Prevalence, detection rates, detection prevalence. We know a third of the samples are for each species, so that's perfect. Accuracy. So this looks like we've taken that data set that we kept, that 20% that this model has not seen yet, and we've handed it to the model to get predictions. Now we're comparing the predictions with the known species. This is an explicit validation of this model, and looking at it, it looks really good. Now let's make a prediction with this model. We're going to define a new data frame, give it the 4 measurements. This is data where we don't know what the answer is. We're going to call predict this model with this new data. It comes back and tells us, I predict this is a Virginica species. There you go. That's it in a nutshell. Now, this looks good. Everything looks good. We're going to save this model. Now, let's actually go step through this exercise in R. So questions? Any questions at this point? Am I going too fast? Am I going too slow? Everybody good? Okay. All right.
I'm very responsive. Yeah. Thank you for asking.
Okay. All right. So I've got RStudio. You know, you can highlight something and click run to run. This is a script. I could run the whole thing, but let's step through it piece by piece. You know, you can highlight it and click run. You can highlight it and click shift enter, or you just put the cursor on that line and hit shift enter, and it'll run that. I'm sorry, not shift, control enter, and it'll run that line. So we're going to load caret. Boom, we did that. We're going to load this data set, this iris data set, which we already have, and we're going to stick it into a variable. So we can take a look at this data set. This is what the whole thing looks like. We only looked at a little piece of it in the actual slides, but yeah, this is what the whole thing looks like. It's 150 rows. It's nothing huge. Now we're going to split it at the 80% mark, so that we have that 20% to go back and use for an explicit validation. All right, and I've just put that 20% into a variable called validation, and we've trimmed down what's in the data set now to be that 80%. So instead of 150 values, we're going to go dimension the data set. It'll show us what the dimensions are. Oh, it's 150. Okay, did I skip something? Maybe I did. Yeah, I did run that. Now it should be 120. Oh, there we go. That looks better. 120 validation has, so data set now has 120 rows with 5 columns. You can think of it that way. Or 120 records with 5 fields. And the validation data set, what we're keeping for an explicit validation and not using to train the model, has 30 records with 5 fields. Let's look at the summary of that. We've seen these numbers. This is the basic statistics and the labels. Let's stuff these into X and Y so that we can do some plots. We're going to do a feature plot, an ellipse. If you've ever seen this before, this is what ellipse graphs looks like, scatter plots. All right. Fox and whisker. That can be useful. It kind of gives you, similar to those dot plots, it gives you an idea of where the mean or median is and what the boundaries are. The other plot that we actually had in the, where the heck is it? Oh, there we go. And this is the plot we had in the presentation. You've seen this one already. So we're looking at the data to make sure we know what exactly it is that we're dealing with. We're going to set those two things of the train control, cross-validation, tenfold, accuracy. All right. Now, let's build our models. Or let's take the algorithms that we're going to use, hand it the data set, tell it what method we're going to train. We're going to train LDA. That's done. We're going to train CART. That's done. We're going to train KNN. That's done. We're going to train SVM. That's done. And we're going to train random forest. And that's done. Now, we're going to look at the resampling. And we're going to do that. And we're going to summarize the results of that. We've already seen this graph in the presentation. Let's look at the dot plot. This is the one that's I think it's visually easier to see and understand this. So, now interesting. So since we're dealing with probability, sometimes you can get different answers. This dot plot looks just a little bit different than what's in the presentation. Now, if you train the same model a second time with the same data, you might get slightly different answers, especially just doing it this very basic way. There are ways to go tune the parameters, and ensure you get consistent results from the training. But just going through the basics, this is a stochastic model, so it's possible to get slightly different answers. They should have similar accuracy. They should be well in the same ballpark, but it's entirely possible to get slightly different answers. So confidence interval 95%. The kappa is the categorization accuracy, reliability, and then the actual accuracy, measured accuracy. So here's some summary information about the model that we chose, LDA. So this tells you 120 samples, 4 predictors, 3 classes, the accuracy from this training session, and the kappa. Now, let's do that. We're going to hand it the validation data set, that 20% that we kept. We've stored that in predictions. We can highlight this and actually look at what's in predictions. So there's the list, the ordered list of predictions. Okay, here's the confusion matrix. We're going to hand it that ordered list of predictions. And this is the ordered list of the known species. Okay, so we're handing it to the confusion matrix, saying, okay, compare these. So there you go. That's what you get. Looks very similar to, it's in the same ballpark as what's in the presentation. I don't know how I managed to get one that was absolutely perfect in the presentation. I guess it was, just probability smiling. So let's do that same exercise. We're gonna stick some new data, one row of new data in a data frame. Okay, so that's stored. And now we're going to hand that to the model and say, okay, do a prediction for this model using the data we put in the new data frame. And there's your answer. Came back as Virginica. That's the answer. We saved the model. All right. So questions? We still good?
Yep, good.
How are we doing on time? 11:38. All right, so we're 43 minutes into it. Okay, so this is pretty good. All right, so we've examined the data to understand it. We trained 5 algorithms using training data. We've validated the 5 algorithms, or well, we didn't validate all 5 actually. We examined one and explicitly validated it. The 5 models were validated through tenfold cross-validation, which is done along with the training. We told it to do that, right? We chose the best model, examined it closer. We ran a prediction with the best model. We saved the best model. So now what do we do? How do we actually use this? So I've noticed that one of the criticisms that R tends to get in comparison to Python in the field is that, well, R is harder to integrate into our into our normal infrastructure. We don't know how to call it. We don't know how to use it, blah, 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 right? Turns out it's actually really easy. This is one of those things that is the perfect model to wrap a REST API around and use it, and, serve it, deliver it as a microservice, essentially. So this is kind of crossing the boundary, though. We've done the data science part of it, which is essentially developing the best model that gives us the best, the most accurate predictions, right? Now we're stepping out of the data science into, I'm using quote unquote software engineering. You can replace that with solution architecture, delivery, whatever you want to call it. We're stepping out of data science into the realm of how do we actually use this? There's several different packages within R that, you can leverage. There's Plumber, there's RServe, there's, RStudio actually has a server edition. You can leverage that. There's a somewhat new multi-threaded package that is really simple to use, and it's called REST RServe. So we're going to take a quick look at that, how you would wrap this and serve it as a REST API. So here's the R code to do that. You got to reference caret and REST RServe so that you have those libraries available. The R code to do this looks like this. It's really simple. It's like 15 lines of code or something like that, right? You define a new application. Now, let's jump from, you define the application, you load the model that we saved in the previous steps, right? So you have that available. Now, let's look at the bottom. We're going to jump down on the bottom. This says serve this on port 8081. And every time there's a request, spawn a new backend to handle the request. That's what this means. And this section here is where you tell it, okay, when this path is hit and the REST API, use this function to answer it. So our function, now let's look at that function, handler. It's a function and has 2 parameters, request and response. We know we're going to get 4 measurements in this, so we're going to grab those 4 pieces out of the REST API call and convert them to numeric, stick them in a variable, and then we're defining what the body of the response looks like. We're going to convert what we get to character, and we're going to call a predict function with those 4 parameters that we converted to numeric here. and we're going to set the response type to this text plain. We can set it to a few different things. Now let's go look at this predict function. Here it is. It's a function that accepts 4 numeric parameters. We stick those into a data frame. We hand that data frame to the model that we loaded, that we had saved, and then we store the prediction. Whoops. We store the prediction, and then we return that prediction. And that is what gets returned here, converted to character and set as the body. Pretty simple code, right? Let's see how you use it. So you save this as a script. Then to run that script, there's a couple of different ways. Probably the easiest way is to just do R script -- I'd put -- vanilla in there so that it doesn't load a bunch of previous libraries, so that you only get the libraries that you actually explicitly asked for. You simply run it with R script. Now, in Linux, you could wrap it in as a systemd service. That's actually really easy to do. In RHEL 7 and above, wrap it as a systemd service so you can service control, start, stop, whatever. This actually, since it uses the rserve package, which I believe is written in C. It's either C or it's bytecode. I can't remember, or compiled from R into bytecode. It's actually reasonably fast. You should be able to get, on good hardware, you should be able to get a couple thousand, a few thousand calls per second. On really good hardware, you might get up close to 10,000. But this is very stateless. So it's very easy to scale it by just adding more servers, more Docker containers, whatever makes sense. So how do you actually use it? How do you call it? Well, let's do that same little exercise. Here we can call it with curl. If I go start it, call it con curl, we can pass it the parameters, we get a prediction back. So let's go try that. I'm going to go back to RStudio. And dang it, this is in my way. Okay. How do I move this? Okay. Oops. That's not what I meant to do. I'm trying to get to. Does anybody know how to move this? Maybe I can. There we go.
The normal WebEx thing?
Yeah, it was stuck in front of me. I couldn't actually get to the menu. So I'm going to launch a shell. This is just here on my laptop. And I'm going to R script. I'm going to run it. I'm going to do -- vanilla. And then that script that you were just looking at, we're going to run it. So it's starting up. It's loading the packages that it needs. It's doing this on my laptop. It's a little slow. Okay. Now we're actually ready to use it. So this session will just sit here and run, until I actually kill this window. So let's go back. Let's go to, you guys can see my screen, right? Yeah?
Yes.
Yes.
Yeah.
Okay, cool. All right, so let's call it. We're just doing a curl, localhost 8081, predict 1. We're passing it the 4 parameters A, B, C, and D. Boom, there's the prediction. Let's change this number to 1. Okay, Versacolor. Let's make this 3.2. That's also predicts Versacolor. Let's make a 3.5. Still Versacolor. Anyway, you get the idea. This is actually very, very easy. This one, I think I've got it set. Let me go look. I think I have it set. Yeah, I changed it to return application-JSON content type. So you can do text plain. There's what, 150 or 250 different content types. I don't even remember what the number is. But there's the code. There's how to call it. This is pretty simple and straightforward stuff, right? Let me kill this so my laptop will move a little faster. Okay, back to this. So you saw some curl examples. You could hit it with your browser. the same way you're doing with curl, you could hit it with a HTTP call from Java or Golang or Python or whatever really toots your horn. It would work for any of them. So this is actually, I kind of say back to my original statement. It's like there's one of the complaints of ours that it's hard to integrate into your infrastructure. Well, I don't know. Doesn't look like it to me. There's nothing. I can't think of many things simpler than just a REST API call. So, okay. So this is the end of the presentation. We've used R to create a working prediction model through machine learning. We've saved it, validated it, trained it, done all that happy stuff. And then we're actually using R to create a microservice that serves predictions from that model through just a simple REST API. So now that's, questions. Open the floor for questions. Let me stop sharing my screen. What do you guys think? Is it good stuff? Useful? Worth learning? Or at least worth seeing, so know when people talk about machine learning, you know what they're talking about, right?
Yeah.
That's the whole reason why I'm on this call. It's simply that.
Oh, yeah.
I'm serious. Vocabulary, understanding. I mean, not that I could do this, but that's not even the purpose. It's the point of the conversation levels, working with development teams, understanding their language and understanding the whole process. So I dig it. I mean, I love this.
Right, good. If you take nothing else away from this, I hope that you take that there's no mystery or magic about this. It's actually pretty straightforward stuff once you understand the basics about it. Now, there's all kinds of complexity that you can go on to handle. Like one of the more complex things to handle are, let's say you wanted to predict when a stock price is going to hit a certain level based on its past performance, right? Mm-hmm. And maybe you've got a history of the stock price. You've got some other things like, market
maybe the average or the lows and highs, right? Last 60-day
like
kind of performance.
I don't know. It depends on what you got, right? Yeah. Market sentiment is something known to affect stock price. So how do you measure market sentiment? I don't know. That's a valid answer. But if you had some sort of data set that was a measurement of market sentiment, you could hand that to a learning model. Now here's the problem. Do you need to predict this over time? Right? Because time series prediction is quite a bit more complicated than just this is like static prediction, what we just did, right? If you want to predict, okay, what's going to be the value a week from now and what's going to be the number a week from now and 2 weeks from now, that's a whole different ballpark, right, of complexity. Doing unsupervised learning, I've got this chunk of data. Okay, I've got data from logs, and I want to try to determine if there have been any kind of security breaches. So I'm going to use my machine learning to scan that data, and I'm going to tell it, classify what you see here into A, B, and C. I don't know what the classifications are actually values are going to be, but I want you to try to cluster it and classify it in some way so that I can gain some insight into, is there even something useful in these logs or not, right, to tell me about security breaches. So those sort of things, right? So fun stuff. So any more questions? If not, I will stop recording, and we can call this a success.
Excellent job.
Yeah, it really is.
Thank you. Well, thank you,
Very
guys.
clear,
focused.
Yeah. Thank you.
All right, cool. All right, well, I'm going to stop recording.